All right, it's the Friday before your break, and I just wanted to touch base on a few items with you guys. First being that after break, the Monday we return, just a friendly reminder, I'm not going to be here. So I'm going to post a lecture for Chapter 6 over your break, as well as some supplemental material from Chapters 4 and 5, mainly reviewing VHDL, really getting into the nuts and bolts of architecture and entities and different constraint statements as to how to code up VHDL text editors, syntax and everything. So that'll be helpful material transitioning into counters, because we're going to find that VHDL is a lot easier than drawing these circuits up sometimes. If we can give it a word description of how we want a counter to function, it's a lot easier than trying to figure out how to wire it up. There's a lot of guess and check sometimes with that. Anyway, so there should be a couple of posts that you guys are going to be watching over your break, a recap of Chapter 4 and 5, and then transitioning into Chapter 6. So I want to go over the exam. And for people in my lab period, the Wednesday you return from break, that first week, I'm going to be attending the lab remotely. So still attend the lab period, whether you want to do it remotely or not, but I'm going to be there via Google Hangouts and doing the lab between 6 and 8. So whether you want to do the lab at VTC or if you have it downloaded on your computer, the ISE program, that's fine as well. So let's get into it. Like I spoke in the beginning of the semester, when you're doing binary conversions to decimal, it's handy to have this table up. This is the least significant bit, 2 to the 0. The biggest mistake on problem 1A was that people called this 2 to the 1 sometimes. Not everybody, but sometimes it happened. But in fact, this is 2 to the 0. The next bit, first one that we're going to add right here is 2 to the 1. So we have 2 to the 2, 2 to the 3 is the next one after that. So we know so far we've accumulated 2, 8. So we know that this number is 10 right here. And then adding to it, 2 to the 4 isn't relevant. 2 to the 5 is, 2 to the 6 and 2 to the 7. So you add these up, 10, 12, 16 plus 8, 4 with a 2 here, 5, 11, 13 with a 1, carry 234. All right, so the next problem the focus was on the other side of the decimal place, and so that's all I'm going to go through. This number is pretty obviously equal to 1, or equal to 7. 3 bits. So there's a decimal place here. We went 0, 1, 0, 1. Okay, there was another 0, but who cares about that, right? So we know that this is 7. We know that this is 2 to the 1/2. We know that this is 2 to the 1/2, sorry, is equal to 0.5, right? Then 2 to the 1/4 is equal to 0.25, okay? 2 to the 1/8 doesn't matter here. 2 to the 1/16 is the next thing that does matter here, all right? And that comes out to 0.0125. 125. We don't have a 0.5 here. This place isn't there, so this is 2 to the 1/4, 2 to the 1/16. All right. So 125 and then 0.625, 0.0625, which comes up to 3, 1, So this was the 2 to the 16, 2 to the 1 over 16, and this was 2 to 1 over 4. All right? Those should have been fairly simple. And the method was in the book, so everybody really should have gotten full credit there. So transitioning to problem 2, we're going the other way now. 53, now we're going to use the remainder method here, and I think the biggest challenge was locating what is the most significant bit and the least significant bit. So the first thing we do is divide by 2, all right? Some people, I think, naturally think the biggest number divided by 2, that's going to be the most significant bit, and that's not the case, all right? So since this number doesn't have a remainder, come all the way over here, this becomes the least significant bit because the remainder is equal to 1. So this is 26 remainder of 1 goes over there. All right, now we're left with 26 divided by 2 is equal to 13. No remainder there. Goes in cleanly, it's a whole number. 13 divided by 2, 6, but with a remainder of 1. Okay, 6 divided by 2 goes in cleanly, we have a whole number again. All right, 3 divided by 2 goes in once with a remainder of 1. All right. Oh, that wasn't supposed to be there. So there was a remainder there. So we're left with 1 divided by 2. It's not a whole number. There's a remainder of a fractional decimal place. So we have 0 with a remainder of 0.5. Okay? But nevertheless, it is a remainder. So here's your number. All right? And for time's sake on this video, B, it's very similar, same process. So let's go to the next page. I wanted you to take both truth tables for an XOR and XNOR gate and complete the following steps, okay? Record both S and POS terms for each gate, okay? Prove that the SOP and POS terms come out to the same thing for the XOR and then again for the XNOR. All right, so XOR, for the sake of time, I'm just going to do the XOR as well. Okay. The exclusivity here. POS term, we're going to add the negated input. Normally this is A naught, but it becomes A because it's negated and it's ORed together. All right, SOP term here. A naught and B the way we normally know it, A and B naught. Again, a POS term, A naught or B naught. All right. Now the biggest, I think people fundamentally understand what's going on here. Some of the biggest problems I saw in this problem was that people transcribed things wrong or didn't negate. Their math was right, their foiling was correct, but sometimes their terms were transcribed incorrectly, so the interpretation was incorrect, but the method for getting the terms was right, so I gave a lot of partial credit there. All right, so first let's, SOP is pretty obvious, it stays true, A and B, or A and B not. POS, product of the sums is A or B, and not or B not. So we FOIL these together, and we get this, outside, inside, first, outside, okay, B not, and then last. The theorem states x times x naught is equal to 0. So what you're left with is right here. All right. Okay, now for the big one. So the grading rubric that I used on problem 4 was, it was worth 20 points. The first page was worth 30 points. Second page was worth 30 points. The last page was worth, 30, 30, 40 for a total of 100, okay? And then the breaking up of the 40 points on the last page was your interpretation of the word description was worth half the points, so 20. All right, and then mutually exclusive of whether or not you got the word interpretation correct, I gave you full credit for your circuit implementation of the expression that you interpreted, whether or not it was correct. Okay, so those two were mutually exclusive items. All right, so going over to the problem, it simply stated, use the following descriptions to come up with the inputs needed to satisfy the circuit described below. Feel free to use any methods, okay? Carnot mapping, SOP, and POS. All right, the method that I would have recommended here would have been to just interpret the inputs, okay, and come up with an SOP expression for the word description that made it true. Okay, so, and I try to put all the inputs in their descriptions in an order which would have made it easy for you guys. So A was the occupied switch for the building, so I would have had that as input A, okay? So A was equal to occupied, A naught was equal to unoccupied. All right. B equals motion sensed. B naught was equal to no motion. All right. C was equal to carbon sensed. C naught, no carbon sensed. All right. D employee. A lot of people came up with truth tables or tried to do Carnot mapping, but since all these inputs for the building were already, think of it as being used in a system that was closed or whatever, we were just sort of tapping off to create a circuit that would alarm during these conditions, okay? We're not creating the whole system for the whole building, right? We just wanted to generate an alarm for a certain set of conditions, okay? So we could just pull from different wires that coming from different sensors in the building to satisfy the following conditions to generate an alarm circuit, okay? A, the condition for A was the circuit will alarm when there is motion sense, and it was bolded for a reason, the building is in the unoccupied state, and there isn't an employee with an RFID card, okay? So I interpreted that as A naught, B, D naught, okay? Building was unoccupied, right? Motion was sensed. No RFID, okay? So there's no employee in there after hours working, okay? The building is unoccupied, but there's motion, okay? This is one of our terms that's gonna generate an alarm. Okay, so also, meaning, or, I didn't wanna make it too easy. I could have bolded or and just given you the whole circuit. Also, the circuit will alarm if the carbon monoxide / smoke detector goes off and the building is in the unoccupied state, okay? So carbon and unoccupied, so C and A naught and C, okay? So this is the second term that could generate an alarm. So we know that this circuit in the unreduced state looks like this. All right. We didn't have to, but you could have pulled out the A naught and done or D naught or C. There's your alarm. Again, I saw a lot of truth tables and people not knowing how to handle. If you wanted to go in after and fill out a truth table for this, you could. You would just have to understand that since all the inputs are mutually exclusive, you don't need all of the input terms. So for example, this term here, all right? If you drew up a truth table, all right? This is true when 0, 0, 0, 1, D naught. When B all of a sudden becomes true, this is the first condition. So, you know, dot, 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 and you get down to here, okay? Which is 5 if you counted it, right? It's 5 Boolean steps, okay? But the thing is, it doesn't matter that we're not observing C here, so they're mutually exclusive, okay? Yeah, they're all inputs on the system, but we're just pulling down electrically from a wire and observing, right? We're observing D, D, and A. So in this sort of scenario, you can say, okay, this is one of my conditions, right? But C at this point is almost like a don't care input, right? So that's why generating a word description, okay, or an expression from the word description in SOP form was the best way to go, all right? Some people tried POS, but there were more 0 terms for the 4 bits than there were 1 term, so it wasn't beneficial at all. So SOP was the correct way to go from the word description. All in all, an average of like an 82-ish, really good. The bell curve was pretty satisfied, so hope you all enjoyed the first third of the semester, and now we're moving on to flip-flops exclusively. All right, thanks. Enjoy your break.